All right, so get ready, because today we are diving deep into supernovae.
Supernovae, yeah.
And you've sent in some awesome research, so I know you're ready to go beyond just the basics, right?
Yeah.
Like we're going to talk about stars dying
Yeah.
and where elements are created,
Right.
and even some hints about the fate of the universe.
The ultimate fate.
Yeah.
Yeah, and what's so cool is that these explosions are actually key to figuring out some of the biggest mysteries in cosmology.
Okay, so let's start with stars. We all know, right, those big balls of gas.
Yeah.
And they spend their whole lives in this constant battle between gravity trying to crush them
Right.
and energy from nuclear fusion pushing outwards.
Yeah.
But that can't last forever, right? That
Yeah.
balance.
No, it can't.
Okay, so you sent over some stuff on white dwarfs, and I gotta admit, the idea of a star that's the size of Earth
Yeah.
but has the mass of the sun is just,
It's wild.
it's mind-blowing. How is that even possible?
Yeah. It's the force of gravity. So in a white dwarf, the matter is squeezed in so tight that electrons are basically packed together. And that creates this pressure called degeneracy pressure.
Okay.
And that pushes back against the inward pull of gravity.
So it's like the electrons are saying, no more.
Yeah, no more squeezing.
But this degeneracy pressure, it has its limits, right?
It does.
What happens if a white dwarf gets, too massive?
That's when you get a type 1a supernova. So picture this. You got a white dwarf in a binary star system.
Okay.
Slowly, it's sucking material from its companion star.
Okay.
And it gains mass, and it eventually hits a critical point, 1.4 times the mass of our sun.
Oh, wow.
And that's called the Chandrasekhar limit.
So it's like a tipping point.
Yeah.
Once you cross that line, there's no going back.
Exactly. The white dwarf just can't handle it anymore, and it explodes in a giant thermonuclear explosion.
Wow.
The whole star gets obliterated.
Okay, so that's type 1a, the white dwarf just going boom scenario. You mentioned there's another type of supernova, right?
Yeah, there's also type 2 supernova,
Right.
and these happen at the end of the life of a single massive star, much more massive.
So these are the big guys.
Yeah, the big guys. Think at least 8 times the mass of the sun, if not larger.
Wow.
So as they burn through their fuel, they get to a point where they can't sustain nuclear fusion anymore.
Right.
And without that outward pressure, gravity takes over and the core collapses in on itself.
Really fast.
Really, really fast.
Okay.
And so the core collapses so fast, it creates this shock wave that basically blasts the outer layers of the star into space.
Okay, so two types of supernovae, both crazy powerful, but with different triggers.
Right.
So we've got type 1a, the white dwarf hitting its mass limit
Yeah.
and exploding.
And then you've
And then type 2, the massive star, core collapse.
core collapse.
Okay. Why should we even care about these? Why are they important to understanding the universe beyond the wow factor?
Right. Well, for one thing, they're responsible for a lot of the elements that make up our world and us.
Wait, so the stuff that we are made of came from exploding stars?
Yeah. So the early universe, it was mostly just hydrogen and helium.
Okay.
You didn't have these heavier elements, like carbon, oxygen, iron, things like that.
Right.
Those were forged in the intense heat and pressure of supernova explosions.
So these explosions, as destructive as they seem,
Yeah.
they're like the cosmic furnaces that created the building blocks for planets and life.
Exactly. And they spread those elements throughout space. So they seed new stars, new planets, and eventually life.
Okay.
It's this cool cosmic cycle of creation and destruction.
So amazing. But you also mentioned that type 1a supernovae are super helpful for astronomers.
Yeah.
They're like cosmic tools. What can we learn from them?
So remember how type 1a supernovae always happen when a white dwarf reaches the Chandrasekhar limit?
Yeah?
Because of that, they explode with roughly the same intrinsic brightness. Astronomers call them standard candles because of that.
Standard candles.
Hmm.
I've heard that, but I never really understood what it means.
Okay, so imagine you've got a light bulb and you know its wattage. If you move that light bulb further away, it's going to appear dimmer.
Right.
Same thing with supernovae. We know how bright a type 1a supernova actually is.
Okay.
So by measuring how bright it appears to us on Earth, we can calculate its distance.
So it's like a cosmic measuring stick. We can use these supernovae to map out the distance between galaxies.
Exactly. And this has led to some really huge discoveries in cosmology.
Like what?
Like the fact that the universe isn't just expanding, it's accelerating.
Hold on, accelerating. I thought it was just expanding, at a steady rate after the Big Bang.
Yeah, for a long time, scientists thought that too. But then, back in the late 90s, there were two teams of astronomers, and they were studying Type 1a supernovae in these faraway galaxies.
Okay.
And they found that these supernovae were actually fainter, which means further away than they should be if the universe was expanding at a constant rate.
So they were like unexpectedly dim light bulbs?
Yeah, suggesting that they were even further away than our models predicted.
Oh, wow.
And that led to this revolutionary idea that the expansion of the universe is actually speeding up.
So what's causing it to speed up?
This mysterious force that we call dark energy.
Okay, now things are getting really interesting. We've got these supernovae, remnants of dead stars, giving us clues about, like, the expansion of the universe, this dark energy thing.
Mm-hmm.
But how do scientists actually study these explosions that happened so long ago and so far away?
So there's this technique called spectral analysis.
Okay.
It's basically dissecting the light from a supernova to see what it's made of.
Okay.
So when a supernova explodes, it emits light across a whole bunch of wavelengths, and that creates what we call a spectrum.
Okay.
By analyzing that spectrum, we can figure out what elements are present in the explosion. We can understand what physical processes are happening within it, and even how fast the material is expanding outwards.
So it's like reading a supernova's fingerprint.
Exactly. And each element has its own unique signature in the light it emits.
Okay.
And by studying those signatures, we can learn what the supernova is made of.
Oh, wow.
And what's going on inside it.
Yeah.
And this also helps us figure out what type of supernova it is and understand those underlying mechanisms.
This is amazing. It feels like we've only just scratched the surface.
Oh, yeah.
Are there, like, specific supernovae that have been particularly insightful?
Absolutely. One of the most famous is supernova 1987A.
Okay.
This happened in a nearby galaxy called the Large Magellanic Cloud.
Uh-huh.
It was the brightest supernova seen in over 400 years.
Wow.
It gave astronomers this amazing opportunity to really study a supernova in detail,
Yeah.
and it actually confirmed many of our theories about them.
Wow. Okay, so we've got Type 1a supernova acting as standard candles to measure distances.
Yep.
And show us that the universe is accelerating.
Right.
And we've got spectral analysis to decode the light, to understand what they're made of and what's going on inside. These mind-blowing stuff.
Yeah.
But I'm sensing there's still more to uncover, right? Like, where do we go from here? What are some of the, big questions that astronomers are still trying to figure out?
One of the biggest ones is this thing called the Hubble tension. It's this weird difference in measurements of the universe's expansion rate, depending on how you measure it.
Oh, I've heard about this. It's, causing a lot of buzz in the, scientific community.
Oh, yeah.
But I'll be honest, I'm a little fuzzy on the details.
Okay, so think of it like trying to measure the speed of a car.
Okay.
Using two different methods. You might track the car's position over time and calculate its velocity, right? Or you might analyze the Doppler shift of its engine noise,
Okay.
which tells you how fast the sound waves are being compressed or stretched as it moves towards or away from you.
So two different ways to measure the same thing.
Right.
The car's speed, or in this case, the universe's expansion. And the problem is, those two methods are giving us slightly different answers.
Yeah. So in cosmology, one method uses the cosmic microwave background, which is that faint afterglow of the Big Bang,
Okay.
to figure out how fast the universe was expanding in its early stages. The other method uses those Type Ia supernovae, those standard candles,
Right.
to measure the expansion rate in the more recent universe.
Oh, okay.
And they don't quite match up.
But if our physics is right, shouldn't these two measurements agree?
You would think so.
Because it's the same universe expanding,
Right.
whether we're looking at it way back when or now.
Exactly. And that's what makes this Hubble tension so puzzling. The difference is small, but it's big enough to suggest that something might be off.
So what are the possibilities? Are our measurements just a little bit wrong?
Yeah, it's possible.
Or is it something bigger, like something we just don't understand about the universe?
It could be either one, and scientists are exploring both possibilities.
Yeah.
Maybe there are systematic errors in one or both of the measurement techniques, but it's also possible that the Hubble tension is telling us about new physics that we haven't discovered yet, something that's affecting the universe's expansion in ways that we don't fully understand.
That's kind of exciting and a little bit scary.
Right.
Like we found this crack in our picture of the universe,
Right.
a hint that there's more to it than we thought.
Exactly. And this leads us to another one of the biggest mysteries in cosmology, and something that might be related to this Hubble tension, dark matter.
Okay, so dark matter. That sounds like something out of a science fiction movie.
It does, but the evidence for it is actually pretty overwhelming. We know that galaxies rotate much faster than they should based on how much matter we can see,
Yeah.
like stars and gas.
Right.
So this suggests that there must be some invisible matter that's providing extra gravity to keep these galaxies from just like flying apart.
So it's like this invisible scaffolding holding galaxies together.
Yeah, something we can't see directly, but we can see its effects.
Uh-huh.
And it's not just galaxies either. You see it in galaxy clusters, the way light bends around massive objects.
Okay.
Even the patterns in the cosmic microwave background. All of it points to dark matter.
Okay, I'm getting it, but my brain is still like, what is this invisible matter?
Yeah.
Is it made of particles we haven't discovered yet?
That's the big question, and it's what physicists are trying to figure out.
Yeah.
The leading theory is that dark matter is made of these exotic particles that don't interact with light or ordinary matter the way that we're used to.
So they're just like passing through us all the time.
Yeah, like tiny little ghosts.
That's creepy and awesome.
It is, and we haven't directly detected these dark matter particles yet.
Oh, okay.
But there are a bunch of experiments happening all over the world.
Really?
Yeah, they're deep underground in mines and tunnels,
Wow.
trying to catch these particles as they interact, even just a little bit, with ordinary matter.
It was like a cosmic game of hide and seek.
It is, with scientists as the detectives.
Wow, that's a huge challenge.
Huge challenge, but finding these particles would be massive.
Yeah.
Not just for cosmology, but for physics in general. It could completely change our understanding of, the fundamental building blocks of the universe.
Okay, so we've got this mysterious dark matter, possibly made of these undiscovered particles, lurking in the shadows of the cosmos.
Yeah.
But how does that tie back to the Hubble tension that we were talking about before? Could dark matter be that missing piece of the puzzle?
That's one idea that people are looking at. Some theories say that dark matter might interact with other forms of matter or energy in ways that we don't know about yet.
Okay.
And these interactions could be affecting the universe's expansion rate.
So maybe these dark matter particles are like subtly influencing the expansion,
Yeah, maybe.
throwing off our measurements
Yeah.
and creating this Hubble tension.
It's like we're trying to solve a mystery, but we're missing some of the clues.
Exactly.
Yeah.
And that's where the real detective work begins.
Right.
The scientists are developing new models, doing simulations, running experiments, gathering more data from telescopes and observatories to try to put all those pieces together.
It's an ongoing process.
It's incredible that we can use these supernova explosions, the death throes of stars, to probe this invisible universe,
I know, it's amazing.
to learn about dark matter, dark energy, and challenge our whole understanding of how it all works.
Yeah, it's pretty mind-blowing when you think about it.
It really is.
Yeah.
And the more we learn, the more we realize how much we don't know.
Absolutely.
Yeah.
That's the beauty of science.
You mentioned some groundbreaking tools that are being developed
Yeah.
to help us tackle these mysteries.
Yes.
Can you tell us more about them? Like, what's coming up for cosmology? What's on the horizon?
Well, one of the most exciting things is the James Webb Space Telescope.
Oh, yeah. Yeah.
It's already sending back these amazing images and data
Yeah.
from deep space. It can see further and more clearly than any telescope before it. So we can study the earliest galaxies and stars and even look at the atmospheres of planets orbiting other stars.
So it's like a time machine.
It is. It's like looking back to the universe's baby pictures.
Oh, wow. What kind of insights can we expect from James Webb about supernovae, dark matter, dark energy?
Well, with James Webb, we can observe supernovae in much greater detail than ever before.
Okay.
So we can learn about their composition, how they expand, and their role in, spreading those heavier elements throughout the universe.
That's so cool. What about dark matter? Can James Webb help us with that?
Well, James Webb can't see dark matter directly, but it can help us map its distribution in the universe.
Oh, okay.
By studying how its gravity affects the light from distant galaxies.
Okay.
So it gives us clues about dark matter's nature and how it helped form these big cosmic structures.
What about dark energy? Can James Webb shed some light on that too?
So James Webb's observations of distant supernovae and galaxies will help astronomers measure the expansion history of the universe.
With more precision. And that will help us understand dark energy's properties and how it's shaped the universe.
So James Webb is like a game changer for cosmology.
It is.
It's giving us this amazing view of the universe and the tools to tackle some of its deepest mysteries.
It's pretty incredible. And when you combine that with other facilities that are coming online soon.
Oh, like what?
Like the Vera Rubin Observatory,
Okay.
which is going to scan the whole night sky every few nights.
Wow.
And the European Extremely Large Telescope,
Okay.
which is going to be the largest optical near-infrared telescope ever built.
Wow. We are entering a golden age of discovery.
We are. It's so exciting.
It really is. All these possibilities. It's just amazing to think about.
I know. It's incredible.
But unfortunately, we've reached the end of part 1 of our supernova deep dive.
Ah.
Don't worry, we'll be back soon with part 2, where we're going to dive deeper into this Hubble tension thing.
Explore this world of dark matter and talk about some of those groundbreaking tools that are going to help us shed new light on these mysteries.
So stay tuned. Things are going to get even more fascinating.
They really are.
They are.
Welcome back to our supernova deep dive. We left off talking about this like Hubble tension thing.
Yeah.
Which suggests that our cosmic clocks might not be totally in sync.
Yeah.
I'm super curious to unpack that more and explore some of the other mysteries that you sent over info on.
Right.
Like this dark matter I keep hearing about.
Yeah.
It sounds so mysterious.
It's definitely one of the biggest puzzles in cosmology right now. It really challenges our basic understanding of how the universe works.
So remind me, what exactly is this Hubble tension? You mentioned it has to do with measuring the universe's expansion rate in different ways.
Yeah, so think about it this way. Imagine you're trying to measure the speed of a car, right? But you're using 2 different methods.
Okay.
One way you might do it is by tracking the car's position over time. Okay.
And then calculating its velocity.
Okay.
Another way you could do it is by analyzing the Doppler shift of its engine noise,
Okay.
which tells you how fast the sound waves are being compressed or stretched as the car moves toward you or away from you.
So we've got 2 different ways to measure the same thing.
Right.
The car's speed, or in this case, the universe's expansion rate.
Exactly.
But the problem is those 2 methods are giving us different answers.
Yes, slightly different answers.
Okay.
So in cosmology, one method uses the cosmic microwave background, which is that faint afterglow of the Big Bang, right?
Right.
To figure out how fast the universe was expanding way back then in its early stages. The other method uses type Ia supernovae, those standard candles we were talking about,
Okay, yeah.
to measure the expansion rate in the more recent universe. And these 2 measurements don't quite line up.
But if our understanding of physics is correct, shouldn't those 2 measurements agree?
You would think so, yeah. Because it's the same universe expanding, whether we're looking at it, billions of years ago or right now.
Right, exactly. And that's what makes the Hubble tension so weird. The difference is small, but it's significant enough that it's something might be a little off here.
So what are the possible explanations? Could it be that, our measurements are just a tiny bit off?
Yeah.
Or is it something more fundamental, something we're missing in our understanding of how the universe actually works?
It could be either one, and both possibilities are being, actively explored.
Yeah.
It's possible that there are just, systematic errors in one or both of the measurement techniques. But it's also possible that the Hubble tension is pointing to some new physics that we haven't discovered yet, Something that's, affecting the universe's expansion in ways that we just don't understand right now.
That's both exciting and a little bit, unsettling,
I know, right? It's wild.
We've stumbled upon a crack in our picture of the universe. A hint that there's more to the story than we thought.
Exactly. And this kind of brings us to another big mystery in cosmology, which might be related to the Hubble tension. Dark matter.
Okay, it's a dark matter. I feel like that's something that sounds like it's straight out of, a science fiction movie.
Right.
This mysterious dark matter.
It does, but there's a ton of evidence for it. So we know that galaxies rotate way faster than they should.
Yeah.
Based on the amount of matter that we can see.
Okay.
Like the stars and the gas.
Right.
And this suggests that there's got to be some invisible matter out there providing that extra gravity to keep those galaxies from just flying apart.
So it's there's this invisible scaffolding holding galaxies together.
Exactly. Something that we can't see directly, but we can see its effects.
Right, right.
And it's not just galaxies either. You see it in observations of galaxy clusters.
Oh, okay.
The way that light bends around massive objects, which is called gravitational lensing.
Okay.
And even the patterns in the cosmic microwave background, it all points to dark matter.
Okay. I'm starting to get the concept, but my brain is still what is this invisible matter? Like, is it made of particles that we haven't discovered yet?
Yeah, that's the million-dollar question, right? That's what physicists are trying to figure out.
Right.
The leading theory is that dark matter is made up of these exotic particles that don't interact with light or ordinary matter in the same way that the particles we know do.
So they're just like passing through us all the time.
Yeah, like little tiny ghosts.
That's kind of creepy and awesome.
I know, right? It is. And so we haven't directly detected these dark matter particles yet.
Oh, okay.
But there are tons of experiments underway all over the world,
Really?
deep underground in mines and tunnels and stuff.
Wow.
Trying to catch these particles as they interact, even just a tiny little bit, with ordinary matter.
So it's like a cosmic game of hide and seek.
It is.
Yeah.
With scientists as the detectives.
And they haven't found anything yet.
Not yet, but if they do, it would be huge. Not just for cosmology, but for physics in general. It could totally change our understanding of the fundamental building blocks of the universe.
Okay, so we've got this mysterious dark matter, possibly made up of these undiscovered particles lurking out there in the universe. But how does that tie back to the Hubble tension that we were discussing before? Could dark matter be the missing piece of the puzzle?
That's one of the ideas that people are looking at. Some theories suggest that dark matter interacts with other forms of matter or energy in ways we don't understand.
Yeah.
And maybe those interactions are affecting the universe's expansion rate.
So maybe these dark matter particles, whatever they are like subtly influencing the cosmic expansion. And that's throwing off our measurements.
Yeah.
Creating this Hubble tension. It's like we're trying to solve this cosmic mystery, but we're missing some of the clues.
Exactly.
And that's where, the real detective work begins, right?
Right. Yeah, exactly. Scientists are developing new models, new simulations, running experiments, and gathering more and more data from telescopes and observatories all over the world, trying to put the pieces of the puzzle together.
It's incredible to think that we can use these supernova explosions, the death throes of stars, to probe this invisible universe, to uncover secrets about dark matter and dark energy.
I know, it's amazing.
And it just challenges our understanding of how the universe works, which is just incredible.
The more we learn, the more we realize we don't know.
Exactly. It's amazing.
Yeah.
Speaking of discovering, you mentioned some groundbreaking tools that are being developed to help us tackle these mysteries.
Yeah.
Can you tell us more about those? What's on the horizon for cosmology?
One of the most exciting things, as we've talked about before, is the James Webb Space Telescope.
Oh, yeah.
It's already sending back these stunning images and data from deep space.
It's so cool.
I know. It's able to see further and more clearly than any telescope before it. So we can study the earliest galaxies, the earliest stars. We can even look at the atmospheres of planets that are orbiting other stars.
So it's like a time machine.
It really is. It's like looking back at the universe's baby pictures.
That's amazing. So what kind of insights can we expect from James Webb, specifically about supernovae, dark matter, and dark energy?
Well, with James Webb, we'll be able to observe supernovae in way more detail than ever before. So we can learn about their composition, how they expand, and their role in, spreading those heavier elements throughout the universe.
So cool. So what about dark matter? Can James Webb help us with that?
Well, it can't see dark matter directly.
Okay.
But it can help us map its distribution in the universe by studying how its gravity affects the light from those distant galaxies.
Oh, interesting.
So that gives us clues about what dark matter is and how it helped form those big cosmic structures.
And what about dark energy? Can James Webb shed some light on that too? No pun intended. I see what you did there. But yeah, James Webb's observations of distant supernovae and galaxies will help us measure the expansion history of the universe even more precisely.
Okay.
And that will help us understand dark energy's properties and how it shaped the universe.
So James Webb is like a game changer for cosmology.
It is.
Giving us this unprecedented view of the universe and the tools to tackle these big mysteries.
And, we've got other exciting facilities coming online soon, too.
Oh, yeah? Like what?
Like the Vera Rubin Observatory.
Okay.
Which is going to scan the entire night sky every few nights.
Wow.
And the European Extremely Large Telescope, which is going to be the largest optical and near-infrared telescope ever built.
Wow.
It's pretty incredible.
That's amazing. We are entering a golden age of discovery.
We really are. It's such an exciting time to be in this field.
It's incredible to think about all the possibilities.
It is.
But unfortunately, that's all the time we have for part 2 of our supernova deep dive.
Don't worry. We'll be back soon with part 3. where we'll dive deeper into the philosophical implications of all these cosmic discoveries.
It's right.
And explore the idea that we are all, quite literally, stardust.
Until next time, keep looking up and pondering those big cosmic questions.
Welcome back to our final part of our supernova deep dive.
Yeah.
We've covered a lot of ground,
And we have.
We talked about the crazy explosive deaths of stars, the mysteries of dark matter, dark energy, and even that, like, cosmic clock discrepancy, the Hubble tension, that has scientists, like, really puzzled.
Yeah, it's a big one.
But going through all this research that you sent, I can't help but feel this sense of awe.
Yeah.
Like just these tiny little specks
Yeah.
in this vast, ever-expanding universe.
It's definitely a humbling perspective, isn't it? Realizing that we're just part of this massive story that's been unfolding for billions of years.
Exactly. And it's not just that the universe is vast, but it's like everything's connected.
Yeah.
We talked about how supernovae create the elements that make up our planet, and even our bodies. Like, we are literally stardust, right?
That's right. Every atom in our bodies, the carbon in our DNA, the iron in our blood, the calcium in our bones, all of it was forged in the heart of a star that lived and died billions of years ago.
That's just mind-blowing to think about.
It is.
Like, these distant explosions, these events that seem so remote and unrelated to our daily lives are actually intimately connected to our very existence.
Yeah.
Like, the universe is telling us a story, and we're part of it, whether we realize it or not.
We are. And it's a story that's still unfolding. Every time a star explodes, it's not just an ending, it's also a beginning, right?
Yeah.
The material that's scattered from a supernova that's going to eventually come together and form new stars, new planets, maybe even new life. It's a beautiful cycle.
Yeah, this amazing cycle of creation and destruction, this cosmic dance has been going on for, like, forever. It's incredible.
Yeah.
Thinking about all this, it really makes me wonder about our place in the universe. We're just starting to, like, really grasp the vastness of it all, the incredible forces at play, the mysteries of dark matter, dark energy. It makes you feel small, but also, like, incredibly lucky to be alive at a time when we're making these groundbreaking discoveries.
I agree. It's a privilege to be able to explore the cosmos like this, push the boundaries of our knowledge, and try to understand our place in it all.
Yeah.
And who knows what amazing discoveries are still waiting out there.
Right.
We're just at the beginning of our cosmic journey.
Well, on that note, I think it's time to wrap up our supernova deep dive. We've explored the science, the mysteries, the philosophical implications of these amazing events.
Yeah, it's been quite a journey.
We've seen how supernovae aren't just destructive forces, but creative ones. They're responsible for seeding the universe with the elements that make life possible. We've delved into those enigmas of dark matter and dark energy, those forces that shape the universe but still remain, like, shrouded in mystery. And we've contemplated the Hubble tension, this discrepancy in our cosmic clocks that challenges our understanding of the universe's evolution. But most importantly, I think we've gained a deeper appreciation for the interconnectedness of everything in the universe.
Yeah.
From the tiniest atom to the largest galaxy.
It's all connected.
It's all connected. And this sense of wonder at the vastness and complexity of the cosmos, this cosmos that we are very much a part of. So to you listening, keep looking up at the stars, keep asking questions, and keep exploring the wonders of the universe. Who knows what incredible discoveries await us in the future?
Yeah, keep those minds curious and those imaginations ignited. Thanks for listening.